Okay, we're gonna next jump into generalized mixed effects models in our mixed effects models unit. So again, no readings for class, but there are some really nice papers and resources here for you in case you're interested in more of the math behind these generalized linear mixed effects models. I think this paper by Ben Bolker and colleagues in Tree is really a nice one. When our data are not normal and we have fixed and random effects, we need to use generalized mixed effects models. So similar to linear models, when you have non-normal data, you need to use these generalized models to account for different distributions of your data. So again, we use the family specification and it follows the same forms and options as linear models. So to remind you, some common types of generalized mixed effects models include, but are not limited to, Poisson models, which are used for count data, right? With a discrete distribution. There's also binomial options for 0-1 data, and also, again, inverse Gaussian function if you have skewed data, but it's continuous. And having just been to the conference in India and seeing a lot of people's work, it really struck me how often we use count data, but we don't use Poisson distributed models. And so I think these generalized models are really important to keep in mind as we move forward. So you use the model statement Glimmer to run these generalized mixed effects models. It's part of the LME4 library. So this is all very, very similar to what we talked about for linear mixed effects models, except for your model starts with Glimmer instead of LMER. And again, it's your response variable as a function of any number of dependent variables plus your random effects. But after you specify your data, you also have to specify your family, which is the distribution that you want. And again, go to the help for $GLMER if you want to see what options are available, but your most likely ones are the ones we're going to talk about. And so we're just going to go through one example here because we went through a lot of examples in the linear mixed effects models on different distributions of data. So I want to just explore one of these in a mixed effects framework. So let's explore this paper that looks at ungulate behavior in response to refuges in urban landscapes in India. It's very interesting timing that this is the paper I found for GLMER on Dryad right after we came back. And so we're going to be talking about black bucks. They are a group living antelopes found on the Indian subcontinent. And the paper that I just showed hypothesized that in urban settings, black buck will be more risk averse when food availability is high and vice versa. And they're pretty cool animals. Sadly, we did not see one. And so the question that we're going to ask with this data is, does black buck occurrence, which is termed black buck in the data set, depend on how open a landscape is, openness, and its resource availability as measured by plant biomass, which is a scaled weight here. The points at which the observations were taken, or point code, should be the random intercept here because, it's sort of like a block or a site effect. The points could be different. There could be something about those points that are not independent, so we want to make sure that we include that as a random effect. And of course, we want to use family equals Poisson because we have count data. So our Glimmer model looks like this. Black buck is a function of openness and scaled weight, plus our random effects, and then family equals Poisson. To get our results, we have to use summary for Glimmer instead of ANOVA, and it's not clear to me how you specify your sums of squares here, so I would just use summary. And when you do that, you can see here that the openness or how open an environment is does not affect the observations of black buck. However, the biomass definitely does, and it seems to be a negative relationship. And we can, again, determine the contribution of the fixed and random effects and their contribution on the variance explained using the variance components. So again, we use the r dot squared GLMM and our model object. And here, unlike the LMER variance components, we actually get multiple types of R-squared values depending on the method used. For example, try gamma or log normal or delta for calculations in the binomial family, which are going to be most of the family types that you use in your generalized models. So, and as you can see here, the results are pretty similar. So just state which method you report when you're writing your results in your papers. Should you use these? So here, the fixed effects explain, again, a small amount of the variance, about 4%, versus the fixed and random effects together, which explain about 60% of the variations. So again, there's a lot of differences in sight. So we will expect to see that in our figure. And we in fact do. So to visualize our results, we plot the black buck occurrence against the scaled biomass and demonstrate the random effects with the different colors. And so you can see that there indeed are quite a lot of difference among the sites. So it's important, again, to include that as a random effect. And I just want to make one comment. There are nonlinear mixed effects models in the same way there are nonlinear models that have no random effects. We're not going to go over them, but I did want to make you aware that these do exist. So in case your data follow different functional forms like quadratic or parabolic, very similar to what we used last time, you can check out the NLMER function in LME4. It's very similar to LMER and GLMER. You just have to specify the function that your data take. But we're not going to talk about it. But again, it's out there. You can look it up if you need. And so with that, please complete quiz 6.2 on Canvas. It's not required for a grade. It's really purely optional, just so I can get an idea of what you're still confused about, so we can talk about it in lecture. And that's the last lecture for this week.